This lesson is an introduction to complex numbers. In your previous math classes, you learned about taking the square root of a number, and you learned how to even simplify radical expressions. So first, let's review perfect squares. A perfect square is any number squared. So for example, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, etc. So it's helpful if you can keep these in the forefront of your mind as you're simplifying radical expressions, because as you simplify them, you want to find the factors inside the numbers that are perfect squares. So these are the perfect squares up to 12 squared. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 squared. So if you were simplifying a perfect square, for example, square root of 25. Of course, the square root of 25 is 5, and that is because 5 squared equals 25. Now in Algebra 1, and some of you also practice this in geometry, if you were simplifying a radical expression that contained a radical, but it was a composite number with a non-radical, or it contained a perfect square, and also a factor that was not a perfect square, so for example, square root of 20. Recall that you would break this down by dividing by the largest perfect square factor that goes into 20. So the largest perfect square factor that goes evenly into 20 is 4. So I would split 20 into radical 4 times radical 5. And then I would take the square root of 4, which is 2, and that would give me 2 radical 5. This is a skill that's a prerequisite skill for the lesson we're working on today. If you need additional help with simplifying radicals in general, you can check in with me at one of my help sessions, or you can find tons of resources online. But today, we're going to be taking the square root of a radical that has a negative inside. And we haven't learned about this yet, although if you had me for Algebra 1, I told you a little bit about it. But this is where complex or imaginary numbers come from. So to take the square root of -1, because that doesn't really exist, we have created a special notation for it called I. And I represents the square root of -1. So when I go to simplify a radical involving a square root and a negative, what I will do is split my square root into -1 times the other factors. In this case, 16 is a perfect square factor, so I don't need to break it down anymore. The square root of -1 is I, so that will come out of my radical as an I. This is a cursive I. And then the square root of 16 is 4. And then we will write this in a simpler way as 4i. Like when we write a number with a variable, we don't write I4, we don't write x3, we write 3x. So we're going to do the same thing here. In the next example, we'll do the same thing. -1 times 81, and the square root of -1 is I, and the square root of 81 is 9. Now the next one is a composite number that is not a perfect square, so we want to break 45 down into a perfect square and another factor. So I'm going to split it into -1 and then 2 factors, one of which is a perfect square. A good rule of thumb for simplifying a radical is to start with about half of this number. So 45 is close to 50, and about half of 50 is 25. So I'm going to start with 25 and see if 25 goes into 45, which it doesn't. And then I'm going to move my way down the list of perfect squares. So next I would ask myself, does 16 go evenly into 45? And it does not. And then I would ask myself, does 9 go evenly into 45? And it does. So I'm going to split that into 9 times 5, which is 45. And so for the -1, I'll bring out an I. For the 9, square root of 9 is 3, so I'll have 3i outside of my radical. And then inside the radical, I'll have radical 5. I know that 5 can't be broken down and divided by any other perfect square factors, so I know this is in simplest radical form. Last one, we have square root of -200, so we'll break that down into -1 and then two other factors, one of which is a perfect square. I'm going to start with about half of 200, which is 100, and conveniently 100 goes evenly into 200. So that'll be 100 times 2, and so this will give me an I and a 10, and so I'll have 10I radical 2. So as we said above, I is the square root of -1, and it represents the imaginary unit. So we're going to practice now simplifying some powers of I. So I to the first is the square root of -1, and when we write it in simplest radical form, we don't want to write it in a radical. The simplest form is actually to call it I. Okay, so when we're simplifying powers that are higher, we'll be dividing, and the remainder we'll be looking for is 1. Anytime we have I to the first power, it'll simplify to I. Next we have I squared. So let's look at I squared. If I expand I squared to be the square root of -1 times the square root of -1, that gives me the square root of -1 squared. And you learned in Algebra 1 that if I square root a square power, those are inverse operations and they eliminate one another. So the square power and the square root eliminate, giving me just -1. So I squared has the simplest value of -1. When we simplify higher powers of I, we'll be looking for a remainder of 2. Now I to the third, if I expand that, I could simplify that to be I squared times I to the first, right? Because 2 plus 1 is 3. Well, I know the value of I squared is -1, and I know the value of I to the first is I. So -1 times I is -I. So I to the third simplifies to be -I. And we'll have -I anytime our remainder is 3. And I'm referring to these remainders, but I haven't really explained where they come from yet, so we'll get to that in just a minute. Don't panic. The last one we have is I to the fourth. If I expand I to the fourth, couldn't I rewrite that as I squared times I squared? So 2 plus 2 is 4. So each of those I squares has a value of -1. So I'm going to rewrite that as -1 times -1, which is +1. So I to the fourth simplifies to 1. And when we divide to simplify the exponents, we'll be looking for a remainder of 0 on that. So in just a minute, we'll look at some problems where we're working with that remainder. Now let's take a look at how the powers of I continue in a pattern. So let's look at I to the fifth. I can rewrite I to the fifth as I to the fourth times I to the first. I to the fourth is a 1 times I, which is just I. Now let's look at I to the sixth. What do you think I'm going to do here? I to the fourth times I squared. Again, I to the fourth is 1, so that's going to be 1 times I squared, which is I squared. And remember, I squared has a value of -1. Let's do I to the seventh. How do you think I'm going to break that down using the powers I already know? I'm going to use I to the fourth times what? I to the third. I to the fourth is 1, so this gives me 1 times I to the third. And the value of I to the third is -I. So 1 times -I is -I. And then I to the eighth, how do you think I'm going to split that one up? I to the fourth times I to the fourth. So that's just 1 times 1, which is 1. Notice that my pattern is repeating. So I had I, -1, -I, 1. I, -1, -I, 1. this pattern just continues to repeat in the same way through the 4 powers of I. We can rewrite any higher power using these 4 basic values. But we don't want to have to count through that pattern over and over and over if our powers are much higher, and that's where the remainder comes in. If I want to simplify, let's say, I to the 50th, then what I'm going to do is I'm going to take that exponent and I'm going to divide it by 4, because that's how many powers of 4 I could get out of this total exponent. So I'm going to divide 50 by 4. And 4 times 12. Actually, I don't want to do this one. Let's stop. Now let's take a look at these remainders. So notice on each of these higher powers, all I did was take out I to the 4th from each of our higher powers, and what was left over was a 1, a 2, a 3, and a 4. And then those represent these remainders for these powers that we're looking for here. So when the leftover power is 1, then I have I. When the leftover power is 2, I have -1. When the leftover power is 3, I have -I, and when the leftover power is 4, I have 1. Next, we're going to take a look at what happens when the powers are higher than that. So when we have exponents that are greater, we could, of course, choose to just count. I to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th. And we would get I to the 1st. But if we don't want to have to do that, especially when these numbers get bigger and bigger, we can also divide to determine the remainder. So you know that each time we get a group of 4, or I to the 4th power, we end up with a 1. So what we want to do is break this down into groups of 4 and then find the remainder. So we're going to actually divide 13 by 4. And then I'm just going to use good old long division to divide by 4. 4 goes into 13 3 times. 3 times 4 is 12. Subtract and you get a remainder of 1. So when your remainder is 1, you have basically I to the 1st power, which is I. You could also think about it like a lot of times you're not using long division, you're using your calculator and you're getting a decimal result. So if your remainder is 1, that's 1 out of 4, which is 0.25. So if you're using a calculator, what you're going to see here is 0.25. Okay? So let's look at the next one, 27. We want to know how many groups of 4 and then what's left over. So 27 divided by 4. 4 goes into 27 6 times. 6 times 4 is 24 with a remainder of 3. So you've got a remainder of 3, or basically I to the 3rd, and I to the 3rd is -I. If you were doing this with your calculator, you would have 3/4 left over. So the decimal you would see would be 0.75. So this could be seen on your calculator as 0.75. The next one, we got 54. We're going to divide 54 by 4. 4 goes into 54 13 times. 13 times 4 is 52. And then we'd have a remainder of 2. And so I squared equals -1. And again, here our remainder was 2. That's 2 out of 4, which is 0.5. So you would see for a remainder of 2, you would see 0.5 on your graphing calculator, or on your calculator, it doesn't have to be graphing. And then finally we've got 72. 72 divided by 4. 4 goes into 72 18 times. Of course, I'm not going 4 into 7 once. 1 times 4 is 4, etc. I'm just saying 4 goes into 72 18 times, and that gives us 72 with a remainder of 0. When your remainder is 0, that means you have all powers, like all groups of 4 with nothing left over. And so I to the 0 is the same thing as I to the 4th, which equals 1. So when your remainder is 0, you won't have any decimal. You'd have like 0.0 at the end of this number if you divided it with your calculator. So here you would have gotten 3.25 because it's 3 1/4. Here you would have gotten 6.75. 3/4 is the same as 0.75. Here, and the fourths is the denominator you're dividing by 4. The 3 is the remainder. The numerator is the remainder, the denominator is the number you were dividing by. So we got I, negative 1, and 1. In these last few examples, we're going to be adding and subtracting complex numbers. A complex number is any number that involves imaginary numbers, and it often includes two terms, a real part and an imaginary part. So all of these with an I are the imaginary part, and that's what makes these numbers complex. But a complex number can have just real, just imaginary, or both parts. So for example, this is a complex number, even though it's just negative 5i. And this is in the world of complex numbers too, although it does not involve any imaginary part. But we're going to be focusing on combining the like terms in these complex expressions. So in order to simplify them, you basically just add like terms, just how you would do if you were working with variables. So for example, 9, we're going to add 3 and 7 because those are the real parts of the expression. And then we're going to add 2i and 6i to get positive 8i. So 10 plus 8i is the simplified form of this expression. On this next one, we're subtracting a quantity, so we're going to distribute the negative to both terms that come after. So I'm going to rewrite the expression. So I have minus 1 and minus 2i. Then I'm going to combine like terms again. 6 minus 1 is 5, and then negative 5i minus 2i is negative 7i. Next one, we have the same thing. We're distributing a negative. So that's going to give me 9 minus 4i plus 2 and minus 3i. 9 plus 2 is 11, and negative 4i minus 3i is negative 7i. Here we have 3 different expressions. We're going to be subtracting the 10 and 2i, and then we'll also subtract 5i, but we don't have to distribute past the end of this grouping of parentheses. So we have 9 minus 10 minus 2i, and then minus 5i. Then 9 minus 10 is negative 1, and negative 2i minus 5i is negative 7i. This last one is a little bit more complicated because we have higher powers of I, and we'll need to simplify those if we can. So first I'm going to distribute my negative. So that gives me 11i to the 4th plus 4i to the 3rd minus 2i to the 4th plus 6i to the 3rd. Then we're going to combine the like terms. So 11 minus 2 gives us 9i to the 4th, and then 4i to the 3rd plus 6i to the 3rd gives us positive 10i to the 3rd. And then we know the value of I to the 4th is 1. So we're going to substitute I to the 4th with 1. So this is 9 times 1. And we know that I to the 3rd is negative I. So we're going to replace that with negative I. So we have 10 times negative I. And so this simplifies to 9, or I'm sorry, it should be 9 minus 10i. Basically, you follow the rules for combining like terms when adding and subtracting polynomials, and then if you have powers of I that are greater than 1, you'll write them in simplified form. Now that you know a little bit about simplifying radicals with imaginary roots, simplifying powers of I, and adding and subtracting complex numbers, pause the video and try these 6 guided practice problems. Then press play and check your work. Here are the answers to the guided practice questions. If you need help, please reach out to me and let me know what I can help you with. If you got all of these correct, you're probably ready to start working on today's assignment. Good luck!